This is problem 37. A pion can be produced by a gamma ray striking a stationary proton. Assuming the pion is at rest, what is the initial gamma ray energy? Well, the proton is stationary to begin with, which means that its momentum is 0, and afterwards the pion is at rest, so the momentum for the pion is 0. And let us say that the gamma ray, which is a photon, is initially going in the x direction. That makes the y component of the momentum 0, which means that after the collision, the y component for the momentum of the proton must be 0, since the initial momentum in the y direction is 0. All right, so now we are going to look at before the collision. We have the proton and we have the gamma ray. And from my appendix on page 4, I have the rest energy of the proton is 938.3. So because, let me just find my paper with all the equations on it. Okay, here we go. So for the momentum, if the velocity is 0, the momentum is 0. And if the velocity is 0, then the kinetic energy is 0 because gamma is equal to 1. And so when the velocity is 0, that means E total is equal to the rest energy. You could also get that from this equation here because the momentum is 0, so E total is equal to mc squared. So before the collision, we have the total energy for the proton is 938.3. And then, because the gamma ray is a photon, the energy is equal to the momentum in the x direction. Now, I know this because I defined the x direction to be the direction that the photon was going in, so I don't have to worry about the sign because I know it's going in the positive direction. Okay, after the collision, we have the proton and the pion. And for the pion, it is a neutral pion, and so we have a rest energy of 135. But afterwards, the pion is at rest, and so the rest energy is the total energy, just like it was for the proton before the collision. Okay, and then afterwards, we still have the proton. The proton has the same rest energy after the collision. So this is before. This is after. And then we're going to look at our conservation laws for both energy and momentum. So for energy, before the collision, I have the total energy for the gamma ray plus the total energy for the proton, which is 938.3. That's equal to the energy of the neutral pion after the collision, which is just its rest energy, plus the total energy for the proton after the collision, which we don't know. Let's call this E gamma, and then for the proton we have E total, we'll call E sub P. That's after the collision, so the total energy is no longer equal to the rest energy. Okay, so we have one equation here and two unknowns. So our other equation is going to come from conservation of momentum. So for the gamma ray, the momentum in the x direction is equal to the total energy. So we have E gamma plus 0 for the proton before the collision is equal to 0 for the neutral pion after the collision, plus the momentum for the proton after the collision. So we want a relationship between the total energy for the proton after the collision and the momentum. So let's go back here. I know the rest energy for the proton. I'm calling the total energy E sub P, so I want an expression for the momentum. I can say E sub P squared is equal to PC. This is in the x direction because the momentum in the y component is 0, plus the rest energy for the proton, which is 938.3 squared, which means for the proton, the momentum is EP squared minus 938.3 squared. Now, question for you. What direction is the proton going in after the collision? If the gamma ray is initially going in the x direction, is it possible for the proton to be going in the negative x direction? That would not be a possibility in this case because the proton is stationary before the collision and the pion is stationary after the collision. So before the collision, we only have one particle moving. After the collision, we only have one particle moving, so it must be moving in the same direction that the gamma ray was moving in to begin with. So this momentum should be positive, and remember this is the momentum for the gamma ray, so that's the total momentum before the collision, so this must be equal to the momentum of the proton after the collision because that is the total momentum of the system after the collision. Well then, this is equation 2. And if I bring the 938.3 over to the other side, then I'll have E gamma is equal to something, and for this equation I'll have E gamma is equal to something, and then I can simply set those equal to each other and then solve. So E gamma is equal to 135 minus 938.3, which is negative 803.3 plus EP. This must be equal to, let's write it again. Is equal to the square root of EP minus 938.3 squared. Now we're going to square both sides and see where that gets us. So this would be 3.3 squared minus 2 times 803.3 times EP plus EP squared is equal to EP squared minus 938.3 squared. Then this cancels with this. Very nice. Then let's bring this over to the other side so that it's positive, and we'll bring this over to this side, so that's 803.3 squared plus 938.3 squared is equal to 2 times 803.3. So let's just write that as EP is equal to this. And then we'll solve that and see what we get. That is 949.6 mega electron volts. That's the total energy for the photon after the collision. 949.6. And then by equation 1, or you can use this. Here we have E gamma is equal to 949.6 minus 803.3, which gives us 146.3. And because that came from equation 1, it should be true that 146.3 plus 938.3 is equal to 135 plus 949.6, and that works. So the total energy is conserved, and now we know that the momentum for the gamma ray is equal to the energy, so this is 146.3, and then from this equation here, we can find the momentum for the proton in the x direction, and that is the square root of 949.6 squared minus 938.3 squared, and that gives us 146.1. Now, it was supposed to give us 146.3, but those both round to 146. So that doesn't look too bad. 146.1 MeV. And we have finished filling out the table. Actually, it only asked us to find what is the initial gamma ray energy, but I would still like you to fill out the table completely for these problems. And that concludes 37. Okay, so I just checked the answer in the book and it doesn't look so good. So this is answer 22 on page 51 of this section, which is 152 mega electron volts. So that's supposed to be the initial gamma ray energy. So we're supposed to get E gamma equal to 152 mega electron volts. Sometimes for these problems, the answer in the back of the book is considerably different than my answer. I suspect that the way that the answer in the back of the book was arrived at was from doing the problem backwards, and rounding does make a considerable difference in these problems. So let's see if the answer of 152 mega electron volts makes sense. So we solved here for the energy of the proton and we got 949.6 mega electron volts. So let's round that to 3 significant figures, so that would be 950 mega electron volts. So if I use the 950 in this equation here, or let's do this first. Okay, so that would be 950 squared minus 938.3 squared, and let's see what that gives us. So that's 950 squared minus 938.3 squared, and then I get 148.6. Oh, that rounds to 149. Okay, but since we only used 3 significant figures for the energy of the proton, let's only use 3 significant figures for the rest energy. So that would be 950 938 squared. So let's try this. What is 950 squared minus 938 squared? And that gives us 150.5, which rounds to 151. So if we do that, then this looks a lot better. This is actually the momentum for the proton, but that should be equal to the momentum for the gamma ray, which should be equal to the energy for the gamma ray. So if we round to 3 significant figures while we do our calculation, then it works out. I do not recommend that you only use 3 significant figures when you do your calculation, but at least from doing this, we can see that the answer in the back of the book makes sense and the way that we solved the problem works. The other way that you could get this energy here is to take this, call it 950, and then use equation 1. So that would be 950 plus 135 for the total energy after the collision. Then subtract the rest energy for the proton, and you get 147, which didn't really help a whole lot. So if you do round, then if you call this 151, the energy is, if you compare the total initial energy to the total final energy, it will be a little bit off. So I think the way that we filled out the table was more correct because we were only off by 0.2, but at least from this we can see that the answer in the back of the book is reasonable. So that is it for problem 37. What I'd like you to take away from this is just if you see the answer in the back of the book and it looks like you might have solved the problem incorrectly, you can always take the answer from the back of the book and put it in to check to see maybe it agrees with your work if you just round things a little bit. So that concludes 37.